I'll be talking about MiG technique using semantic compression for efficient migration of desktop VMs. This is joint work with Anshul and Ashok, Anand, who are now in startups, making me do the presentation, and Venkata and George, who are still with Microsoft. Okay, so most people are familiar with server VMs migrating. Some of you might ask, why do you want to migrate desktop VMs, right? So here is one scenario which I would really like. This is the scenario of a single desktop environment that is always running and always local. That is, when I'm interacting with it, it runs on the machine that I'm at. When I'm not, it is always running, right? And this gives a seamless computing experience, which a lot of people have talked about, and does not sacrifice the interactiveness of a local responsiveness, right? And this is possible if you can encapsulate the desktop in a VM and have it move around so that it is always near where you are, right? So that's one use of a desktop VM. And some of you might think this is quaint in today's cloud obsessed world where there's no desktops, there's only cloud. Well, even in a cloud desktop setting where desktop is just a service, you would still have the desktop in a VM and they would be moving around, but maybe not near you, but on servers that are close to you, again, so that you have quick response when you interact with it. So desktops can move there as well. And finally, it's also been used, desktop migration has been used for energy saving, where the idea is your PC, when it goes to sleep, the desktop can be parked on a server, and then you save energy while you don't have a disruption, which sleep typically provides. So there's lots of benefits if you have this notion that your environment, the whole computing environment is a VM which keeps moving around. So what is the biggest drawback or challenge which makes this not happen today, right? The biggest reason we believe is that these desktop VMs have large memories, 4 GB or 8 GB or more, and moving that is not very efficient today. You look at, there are two aspects to this. One is the bytes transferred. So imagine my scenario where I go from home or work every day and my desktop keeps moving around with me. We are talking, say, 200 GB or more of traffic over a month. And many of us have tiered bandwidth plans where some start as low as 10 GB and this would be very expensive. But even more important than bytes transferred is migration time, right? When I'm home, I quickly want the VM near where I am so that I can do something. And that, for a 4 GB VM, can take an hour or more, right? So reducing bytes transfer can help, but if you do heavy-duty compression, it might actually be slower, and you might save bytes, but you may not reduce the time transfer. So you really want to optimize both these metrics. And I just want to say, disk state also needs to be migrated for this scenario, but some studies have shown that this typical dirty disk state is smaller than the memory dirtying, and for this talk I'm going to assume the disk state gets synced independently, but there's some work on that as well. So how would you do this? How would you address this challenge? So we started with this approach. So if you think of desktop VMs, right, unlike server VMs, there's a human interacting with the desktop, and the input is in the form of keyboard, mouse, and so on. There's like small amount of input that we provide, right? We type or we click on an app and launch it. The small click can launch an app which can create a large amount of memory dirty, right? And so the intuition here is, if you can replay this input, you can create similar memory at the destination, and then all you have to do is send a small delta to make sure they are in sync. So you can do very efficient migration by replaying maybe a few bytes of input and create memory similarly. So this was our intuition, and if you look at some of the prior work in the space, this sort of seems like a promising approach, right? I mean, if you look at difference engine where there are lots of similarity between VM memory, or for example, the opportunistic replay work, it seemed like, intuitively, if you just launch the same app there and do the same things, your memory should be very simple. And we were really shocked, and we actually assumed that would be the way to get efficiency. And as we went this process, we were really shocked that that was not the case. And so in this process, we sort of developed different techniques for doing efficient migration, and here is a summary of our contributions in the paper. The first thing we found is input replay is not really effective for VM migration. So this is sort of a negative result, and the reason is that replay is impeded by lots of randomness and non-determinism, which happens due to these new features in OS, which are prefetching and security related. I'll go more into that later. The second thing we did was, as we dug deeper, we found that if you can leverage the semantics of the memory pages, this is a free page, or this is a heap, or this is an image, you can do much better in terms of migrating the VM. So you don't need replay, but you can parse the pages, you can do much better. And finally, we have implemented this on Hyper-V, and we get about a halving of the bytes transferred as well as reduction in migration time compared to gzip, which is what is commonly used today in most VM migrations. Okay, so let's start with this simple experiment, right? Very simple. We launch a VM, boot up a VM, launch typical Office apps, right? And first question we want to ask is, we have two workloads, a short workload and a long workload, one which is 30 minutes and one is 3 hours. And all we want to see is, what does the memory look like across different versions of the OS? Because some of this earlier work was done in 2008 and used older versions of the OS, right? Simple question. And this is what we found. A lot has changed since Windows XP. So here on this table, I have 4 different versions of OS. So let's first focus on Windows XP and Windows 7. On the rows, we start with a blank VM, short workload, and long workload. What you see is that this is the number of 0 pages in a VM, right? 5 years ago, if you did a lot of work, the number of 0 pages can still be a large amount, 72%, right? What modern OSes do is obviously figure out, we are wasting this memory, might as well see if we can optimize and use it. And so the number of 0 pages dramatically goes down over time. And as the first speaker was saying, right, Windows does lots of things in background, and that's true. It is trying to make full use of the memory space. And so if you run the same workload on 2 different OSes across time, you see this dramatic reduction. And the case with Linux is similar. There is something called preload, and which also reduces the number of 0 pages, but just not as aggressively. So what has changed? So this is a process in the background called Superfetch in Windows and preload in Linux, which basically tries to make full use of the resources of the VM, right? If you have 2 GB or 4 GB, let me use it by prefetching things which you might need maybe, and I can reduce your response latency. So this is great for user responsiveness, but what this does is uses up your memory, does a lot of work, and as we will see, that will impede replay. So second experiment, we boot up 2 identical OSes now, same Windows 7, 2 identical Windows 7 for example. We launch identical applications, same short and long workload, and now we are providing input to these applications automatically in 2 ways. One is paced, which means if I'm booting 2 OSes, one workload took 3 hours. In the replayed version, I also take 3 hours to replay the thing, which is just the ideal scenario. So you're talking about everything going right there. And the accelerated replay, where basically I'm replaying the input that you have provided in a very short amount of time. This is what we would use if we wanted to do migration using replay. We would take the input, play it in a minute or 2, get the similar state, and hope that we can sync very fast. And now we're going to compare the 2 versions of the identical OSes. Okay? How similar are these? And before I started this project, I assumed they would be highly similar. We have tried to control as many things as possible. What this shows is the percent of identical non-zero pages between the 2 VMs. So each column there is Windows XP, means there are 2 Windows XP VMs which are running the workload on each row. Windows 7, we are again comparing Windows 7 with Windows 7. Same thing with Debian. We are comparing identical OSes, identical workload. And what you see is, even for a blank VM, there were 66 identical pages in Windows XP. That's come down to 33%. And in fact, as we go further, it's going to get lower and lower. the pages which are identical comes down even with a blank boot up VM, and as you get the long workloads, the number of identical pages goes down to 14%. So we are doing everything the same, identical pages go down. So then we said, let's look deeper, let's look at partial page matches. So here again, there are two graphs, one for XP and one for Windows 7. The x-axis is page similarity. So we take 2 or 4 GB VM. For each page, we try to find the best page on the other replayed VM where most of the bytes are identical. So 0 to 127 says very few bytes of a page are identical. 1024 words says all the words in this page are identical to that page. Right? So rightmost in each graph shows pages are identical, leftmost says pages are very different. I couldn't find any match. And with Windows XP, about 85% of the pages are identical or almost identical, say the last two bars in that graph. With Windows 7, the number is 38%. So we have done pretty much the same app, same input, the memory is very different. Why is that? Obviously, Superfetch is playing a role, but the other thing which is playing a role is ASLR, which is address space layout randomization. So this was added after XP for security reasons, and basically it randomizes the load address of executable heaps and so on. The effect of that is any pointers in your page to other heap location or other libraries will change across two independent OS boots, right? So what this does is creates lots of small holes in a page which are very different. That added with Superfetch makes two identical OSes very different, right? So what this showed is replay is not very useful. In fact, we did even more investigations which are there in the paper. I'm just summarizing here. Partial matches are not clustered in Windows 7, they are spread throughout the page. So if you want to use a replay, you have to do like fine-grained chunk matching. We tried to do rsync, which is for syncing files on the replayed VM and the original VM. You do get a little bit of gains if you use very small byte size chunks to do the rsync, but then it becomes very slow, 13 times slower than gzip, for example. We tried different compression tools, bzip2, 7zip2, and so on. They do better than gzip, but they are much slower. So the question we asked was, okay, this sort of looks like a negative result. So one approach is, say, we can disable or modify these Superfetch and ASLR and so on, and then try to do efficient migration. That might have implications in terms of performance and security, but that's one way to go. Or can we do it without it? And thankfully, we found that if we can tailor the migration to the semantics of the memory page, we can indeed do better without having to disable Superfetch or ASLR and so on. So this is the key idea of the paper, is to understand what is a page and do things according to it. So how did we arrive at that? So if you look at the pages of a VM, there is heap, there is image pages, the kernel pages, and Superfetch or these prefetch pages which can be data or image, mostly one of the two, and there are free pages. If you just did gzip on the whole image, you get about 2/3 of compression. But you can see that some pages are more compressible than others. So for example, Superfetch is not as compressible, so can we do something for that? Heap is highly compressible, so each page has a different characteristic. Free pages, for example, is 80% compressible, but really we don't need to send them at all. The other side does not need to know that this page is identical, right, for example. So here is the design for MiG. So we first parse, identify each page by its type. Free or zero pages, we suppress them. We also do a full page match, so we found that 33%, for example, was identical. So we take a blank VM and do a full page match. If the pages are identical, we can just send a hash over. So that's the simple part which people have proposed in the past. Then for image or Superfetch pages, really the data comes from the file system. So what we do is we use that context to do a diff on the page. Data comes from the file system, but some things might change because there are pointers or other things, so it won't be identical. So we need an intelligent way of doing diff, which is what we do. And then for heap and other pages, we do something where we take the whole VM and find redundancy in it to do better than gzip. So let me just tell you about a couple of these things, a little more detail. So what is image superfetch page? Context specific diff. So the superfetch is basically trying to take state in the disk and keep it ready so that the user can use it at any time of day or what he's going to use it, reduce the response latency. So what we do is we take this context, both sides has this context, these are common like executables and DLLs which are there in the file system, preload it and index it, saying chunks in this have, we build a table of chunks which are already there in this. Then when we see a memory page which is an image, we just fingerprint it and then find if those chunks in those image are already present in this context. If they are, then we don't need to send those chunks. We can just send pointers saying to the other end, go back into your context and retrieve these chunks, right? So it won't be identical. The chunks will be varying length and varying size. So we modify something called NDARI, which was an SDI 2010 paper, to augment it with this knowledge of a context in order to do this efficiently. And the next thing is heap pages. So it already compresses well because it has lots of zeros. But we found that there is even more redundancy typically in the heap pages of a particular process. So if you take all the heap of a particular process, there are lots of redundant bytes which are non-zero. But in the normal layout, the heap pages are spread arbitrarily throughout the physical page. So if you just apply gzip, which has a small 64 kilobyte window, it's not going to capture this redundant bytes. So instead what we do is we have an intra-VM redundancy layer which indexes the heap throughout the large VM space and then finds redundancy which are over a larger history. Okay, so we have implemented MiG on Windows Server 2008 Hyper-V, and really it has two pieces. It examines the guest VM memory to extract the semantics, and then once you have the semantics, we apply the technique tailored for it. So first thing is in Windows, there's a database called the page frame number database, which has metadata on the pages, page type and so on, and also a reverse mapping into the process virtual address space, from which we can find out what the process virtual private spaces are. These are well documented data structures that we use to extract this information. So this is OS knowledge, but sort of public OS knowledge of how the pages are architected. So once we extract that, we apply the technique for that particular page, and we migrate the page. So let me go into evaluation. We look at desktop VMs, real user workloads as well. So from a lot of our colleagues, we just took a dump of their memory and tried to do the analysis. We also created artificial workloads. We use both Windows and Linux for our evaluation. And we look at two metrics. One is the byte savings on top of gzip. That is, gzip might already be reducing your VM size from 10 to 5 GB. What are the savings we get on top of that? So that's our saving metric, and the other is migration time. So here is a graph which shows the savings. The x-axis is 10 different Windows workloads of varying memory size that users had on their desktops, and the y-axis is the byte savings that we get. So the first thing is across these workloads we see about 40 to 60%, about 50 or more average savings for all users compared to gzip. So this is extra savings on top of applying gzip. And as far as our techniques are concerned, we have these different techniques, 4 different techniques of free pages, full pages, and so on. And you can see in this Windows case, the intra-VM redundancy for the thing which we did for heap really dominates, gets 30 to 40% of the gains. Context provides only 10-15%. On the case of Linux, so these are 5 Linux desktops, the gains are similar. We get 60% byte savings, and the difference is the techniques, some of the techniques vary differently. So here in this case, full page matches contribute a lot more, And that's partly because the randomization for ASLR used in Linux, at least in Debian, is not as comprehensive as what was used in Windows 7. So you have a lot more page matches. So full page contributes more, and context contributes a lot more here compared to Windows. But again, the overall savings is about 50 to 60% in bytes. Finally, migration time. So this is one example of a VM, 2 GB VM on a 10 megabit per second link. And you can see the 2 GB VM on using just gzip would get you 2/3 compression. So you're at 670 megabytes, which compresses much faster in 65 seconds, and the transfer time takes about 550 seconds. Whereas with MiG, we can transfer it in 275 seconds, and we get half 50% or 100%, I mean half the time for migration and half the bytes that we do, right? And our prototype is, again, it's just a prototype. We can do more optimization to speed it up. It takes about 67 seconds because we use WinDebug APIs to do the parsing of the page semantics. We think we can do better and optimize it further. Just as a point of comparison, again, if you use other compression tools like 7-zip or bzip2, it does reduce better than gzip, but it's much slower. So you're now going to save on migration time. And finally, we can split this into multiple cores and speed it up that way to get at least 100 Mbps link. We can retain the 50% advantage. So there are other results which I'll refer to in the paper. Just to summarize what they are, we also went back to our original scenario of back and forth. That is, I go between home and work. What happens when those scenarios, we can get much higher savings there with absolute, I mean, if you're short amount of interval, if you've just gone for an hour, the deltas are, you can do about 90% absolute or 95% absolute compression. We also evaluated the impact of ballooning. What happens if you balloon and throw out less important pages before you apply MiG? We still found savings there. We also looked at impact of varying aggressiveness and prefetching, whether more aggressive prefetching will hurt us. It does not. You can do as much prefetching as you want. Your savings will still remain. And we also did this MiG replay, which is MiG, but which used a replay VM to see whether we can do better. And there are a lot more results in the paper on those. But I will not go into that for lack of time. So to summarize, really the three key messages: input replay is not really effective for desktop migration because they are impeded by the randomness and non-determinism induced by prefetching and ASLR. So in modern OSes, input replay is not very effective. The second is, if you can use the page semantics, you can do much better in migration. And for example, we have it on Windows Server Hyper-V, where we can half the time and the bytes that you transfer compared to gzip. With that, I'll thank you and be happy to take questions.
Hi, Konrad Miller from Karlsruhe. In the beginning, you said you would transfer the bytes from the hard disk out of band, and you have some synchronization mechanism, and that's fair enough as it doesn't change very often, libraries, programs, and so on. I was wondering throughout the talk why you wouldn't just drop all the pages that come from disk and not transfer them, just load them from the local disk that was synchronized in any other way.
Yes, that's a good question. I guess I should have mentioned. The problem is, for example, these pages which are loaded from disk or into memory, that information is hidden somewhere in the memory. So if you don't transfer them, it's going to substitute a garbage page in there instead, right? So there are data structures which point to what is happening in the Superfetch thing. If you don't change the data structure and not do the pages, you're not going to get it.
So you need the memory balloon to zero those pages.
Yes, so you could memory balloon, so we have those results as well. But the problem with these pages are these are not low priority pages. So there's a page priority, and some of these pages are high priority because the user is very likely to use them. So they don't balloon only these pages, they balloon other pages as well. And how much you balloon is a trade-off. So again, there's an orthogonal technique, but they can help, yes.
Right. Thanks.